Okay, so this is what we worked on, and I just wanted to make sure everyone has the answers. There was some audio difficulties, so I'll put this out there. We're talking about phases and phase changes, the different states of matter. You've got your solid, liquid, gas, and this is a phase diagram that you want to be familiar with. It just shows kind of how things react under different pressures and different temperatures. Um, so if you are on the line here, that means you are in both states. So here you have your gases and your solids, all right? So if you're right here at 500 degrees Celsius and 20 degrees, or excuse me, 20 atmospheres, that would put you right here. So that means the state you would be in is a gas, all right? Um, if that you have that same compound, right, this mysterious compound X, if this mysterious compound X is at 100 degrees Celsius and a higher pressure, 50 atmospheres, it's right here, that would be in the solid state, okay? And this point right here, as you go from one to the other, right? As I go from a solid to a gas, remember that would be sublimation. And as you go from a gas to a solid, because it goes both ways here, this would be deposition, right? And that's how this works. And so here you have at these temperatures, all right, it's going from a liquid to a gas and a gas to a liquid. All right, so liquid to gas is like water evaporating, right? Turning to water vapor. So that's evaporation or vaporization. And going from a liquid to, a gas to a liquid, that is condensation. Okay, like when your water vapor turns into a liquid on your cold glass. All right, then you have this line right here, which is in between a solid and a liquid. So if you're going from a solid to a liquid, you're melting, right? I think ice to water, that's melting. If you go from liquid to solid, that would be freezing, right? If you have water and you are making ice, then that is going to be, you put it in the freezer. So that would be freezing. So freezing and melting are opposite phase changes. All right. Evaporation and condensation are opposite phase changes. And then sublimation and deposition are opposite phase changes. So that's why this is called a phase diagram. All right, so there are a couple points here that are very important. One is called the critical point, and that is this guy right up here. All right, that's the critical point where you cannot tell if you're in between a gas or a liquid. All right, here's your liquid here. It's a gas and a liquid. That is the critical point. And this says what is the temperature there? Well, you take your critical point, follow it down to the axis that is temperature, right? Because this says temperature. So that would be in between. So we'll estimate, I'll say 750 degrees, and my units here are Celsius. All right. The next question, it says, if you were to have a bottle containing X in your closet, what phase would it most likely be in? All right, so the phases are solid, liquid, or gas. Well, if you have, if you're in the closet, it says you've got a low temperature and a low pressure. So that would be down here. All right, so in your closet, you have like 1 atmosphere. All right, so you're really low pressure. And because this is 10 atmospheres here, so you're even further down here. So that would definitely be like down here somewhere. So that would be a gas. All right, because it says what phase. So if you have very low pressure, then that is going to be a gas. All right. At what temperature and pressure? So we're looking for temperature and pressure where you have all three phases, okay? So we have your critical point where you've got liquid and gas at the same time. Then you also have this point right here where all three are meeting, and this is the triple point where you have all three phases at the same time, all right? That is the triple point. And so the question, though, is what temperature and pressure? You always got to make sure you answer the question. So here's the triple point. The temperature would be about 350, and the pressure, if I come over here, would be about 50. Okay, 50 and 350 for temperature and pressure. So 350 degrees Celsius. Oops, wrong question. 350 degrees Celsius for the temperature, and the pressure at this triple point was 50, right? If I come over here and look, because this is my pressure axis, so that would be 50. And the units for pressure on this chart are atmospheres. Okay, so let's erase this here. All right, so number 4, it says, what if I have a bottle of X at pressure, it gives me a pressure 45 and it gives me a temperature of 100. All right, so then it says what will happen if you raise the temperature to 400 degrees Celsius. All right, so I've got a pressure of 45. So this is kind of a mess. Let's erase this so we can see what we're doing here. All right, that's probably enough to be able to see what we're doing. Okay, so the pressure is 45 and the temperature is 100. So when I'm at 45, here's 40, 50, so 45 is in the middle, and the temperature is 100. So if I come up here and over to here, that's this point here. Well, what state is this? That would be solid. Okay, so my X compound is solid here. Now it's saying that I'm going to raise the temperature to 400. So 400 is over here. Well, if I stay at the pressure of 45, but the temperature is 400, I'm right here. So that is in this area right here. Gas is this whole area here is where you're a gas. Okay. Liquid is this area right here. Solid is all these points right here. We're looking at that whole area. Okay, so this point right here is definitely in the gas area. So that would be a gas. So it says, what will happen if I raise the temperature to 400? Okay, it goes from solid to gas. All right, so now it says, why can't X be boiled at a temperature of 200 degrees Celsius? So let's look at what's happening here, and I've made a big mess. Let me see if I can erase all this. All right, so if we have a temperature of 200, what's happening? So here's the temperature of, right, temperature is this axis, so this is 200. So it says, why can't X be boiled? Well, boiling is where you're going from, you've got a liquid, right? Like if you're boiling water, you have a liquid and you're going to a gas. That's boiling, all right? It's kind of like evaporation. So I have to be a liquid to a gas. Well, at 200 degrees Celsius, all these points, it's a gas. Right here, it's going from a gas to a solid. And then right here, it is solid, solid, solid. So at 200 degrees, it's either a gas or a solid. Okay, or both, where it's gas to solid, remember, is deposition. All right, so I'm either gas in that phase change of deposition, or I'm a solid. Deposition is like when you have frost, where the vapor, the water vapor in the air freezes and becomes solid ice on your car or on the grass. That's deposition. So it can't go from a liquid to a gas, okay? Because at 200, X is either a gas or going through deposition or a solid. All right, that is all it can do at 200 degrees Celsius according to this phase diagram. So if I wanted to, could I drink X? Well, to drink something, it has to be a liquid, right? So when is X a liquid? Well, let's go up here. So again, I'm going to erase to make this a little bit clearer. So when is X a liquid? I need to practice my erasing. So liquid is from, is this area, right? Here's where it's going from a liquid to a gas or a gas to a liquid. All right, all these points in here is where it is a liquid. So the question is, well, what temperature? So if I come down here, here's my triple point where it's all 3. Come down here, that's about at 350, right? At 350, it starts being a liquid, and at 750, we said, is where it's the critical point where you can't tell if it's a liquid or a gas. So between 350 and 750, that's when it is a liquid. Well, can you drink something this is degrees Celsius, even Fahrenheit, right? That's hot. 100 degrees is boiling. So no. All right. So no, because it's a liquid. Oops. At 350 degrees Celsius to 750 degrees Celsius. All right, too hot. All right, and that is, well, I guess we actually did this second page here too. So now that's talking about phases and phase changes. And this is another diagram where you can see this is a heat curve. You can see this is solid phase, liquid phase, gas phase, right? And this is your phase change, all right? This is your evaporation, or what the opposite was condensation. This was your melting and your freezing, okay? But if you look at what your axes are, you're talking about energy. And a big thing here is energy is in joules. Okay, that's a new unit called joules that we've learned. All right, so here we're increasing the energy and looking at what happens to the temperature. All right, the y-axis here is temperature. So you can see when you are in a state, okay, like here's the solid, right? When I have a solid and I increase the energy, I heat it up, right? It gets hotter. The temperature goes up. All right, if you have a liquid and you are adding energy, it gets hotter and hotter and hotter. If you have a gas and you add energy, it gets hotter and hotter and hotter. There is a change in temperature. All right. When a temperature goes up, that means you have a change. That means delta. Delta means a change, and then T is for your temperature. All right. So in these states here, your temperature changes when you add energy. It gets hotter, okay, or cooler. When you have a phase change, the interesting thing is that the temperature stays the same. All right. But you are adding energy. So there's a same temperature, the delta T, right here, my change in temperature is 0. There is no change in temperature. All right, the change in temperature here, change in temperature is 0. It's staying the same temperature, but I'm adding energy. All right, so what is changing is the energy. All right, and that is what enthalpy is. Okay, enthalpy is the amount of energy that is absorbed during your phase change. Okay, or released during your phase change. So, and that depends on what it is. If you have, each different compounds can absorb different amounts of energy. All right, so that's what enthalpy is. Specific heat capacity is when you are staying in the same state, so your water, but it's saying how much energy can this water absorb. That's the specific heat capacity. All right, it's the amount of energy that you can absorb. All right, and it varies depending on what it is. It's just like a person, like how much heat can you take? We're all different. All right, so liquid water can absorb a lot of heat. It has a very high specific heat, and that is why it cools off the earth. All right, it can absorb all this heat and still stay as water. Then you have, if you have solid water, all right, which is ice, ice can absorb heat, energy, right? It's a solid, here's your ice. It's absorbing energy, but it can't absorb as much. It's a lower specific heat. And then if you have vapor, it's kind of in the middle. It can absorb more than an ice cube, but less than liquid water. Okay, so specific heat capacity is like how much can you take? All right, if I fill something to capacity, if I fill a stadium to capacity, that means it's full. So specific heat is, well, how much heat will fill this thing up, whatever it is. Solid, liquid, water, whatever element it is. All right. So here we talk about calculate the heat required, and we have a different variable for that. It's called Q. All right, Q is the heat required. And the heat required depends on 3 things. All right, if you're going to, it depends on how much you've got. Think of if you're grilling, right, some food or cooking food. How much heat you need depends on what type of food it is. All right, so, and how much you've got. So let's say we have, so that would be the mass. All right, so here I'm given a mass, and I am given 2 temperatures. All right, if I have 2 temperatures, I can figure out the change in temperature, right, by subtracting the high temperature minus the low temperature. All right, and that equals 25. The difference between -25 and 0 is 25. All right, so that is the change in temperature. The other thing that determines how much heat is required, all right, to change the temperature is the heat capacity, the specific heat capacity. And that varies. So you need to know what you're talking about. My element here is ice. So the specific heat capacity for ice is 1, and that we'll use C for the heat capacity. All right, and that is what's given here. Specific heat capacity, that's my C. All right. So now you write your equation. All right. It kind of looks like Q equals MCAT. And then you substitute in. All right. If you can do algebra, you can solve anything. So the mass is 1250. The heat capacity is 1.84. The change in temperature was 25. There's no symbols in here, so that means they're all being multiplied together. All right, and then you would just go on to your calculator and figure out what what the product is after you multiply all. Now, when I went to get my calculator, I erased everything, so I'll write it back on here. Oh, and I got to open it with Cami. I would suggest that you all get, I love this app to be able to write on a PDF. It's really nice. Oh, and there it is. There's my stuff. All right, so I'm going to put in 1250 times 1 point, my heat capacity. All right, so mass times the heat capacity times the change in temperature. And that gives me 57,500. And the unit, right, if I'm looking at heat, remember the heat is joules, so that would be joules. All right, and if I want to write this in scientific notation, I could say 5.75 times 10, let's see, that would be 1, 2, 3, 4. 10 to the 4th joules. All right, and that is what we practiced today. All right, I'll do the next one because it has to do with enthalpy. So this had to do with specific heat capacity, all right, because we had a change in temperature. But if I'm melting, right, remember melting means the change in temperature is 0. So if I multiply by 0, my heat is 0. All right, so I'm not using the change in temperature because there is no change in temperature. I'm using the enthalpy. All right, so I'm melting, so that is fusion of water. All right, so, and that is very similar. It's the heat, right, because it says calculate the heat. That depends on the mass, just like with the first one. But not capacity, heat capacity, it's enthalpy. So what is the change in enthalpy? What is the change in energy as I go from here to here? How much energy was added? All right. So my mass is going to be 1250 again. So 1250. And the enthalpy, the change in energy to melt the water is 333.51. All right. And then I'll just put that into my calculator. And I'm going to multiply 1250 times 333.51. All right, so I get 416,887.5, which I'll just leave that as that. All right. If I want, let's say I wanted 3 significant digits, right? Since this is 3 significant digits, I'll say that's 417 or 4.17 times 10 to the 1, 2, 3, 4, 5, 10 to the 5th power. Right, I rounded the 6 to a 7 because of this 8 here. Right, that's bigger than 5, so that bumped up to a 7. And then that would be joules. Right, you'll have multiple choice questions, so as long as you can go back and forth, you're good to go. All right, so have fun, keep practicing. These are easy. It's just a formula. You just substitute in.